So I said we were going to start multiple regression, and that's what we're going to do today. We're going to add another predictor variable, another x variable to our model instead of just one x. And I thought the simplest way to do that is by just adding a binary variable, one that can be coded as 0 and 1. So it's a very simple variable to and add it to a quantitative variable that we already in the regression, and explore how it's often used. I mean, often we add another variable to remove confounding. And so we're going to try to, in this example, in this next few chapters, I'm going to show you how adding a variable to another variable to a regression model, sometimes it's called adding it as a covariate, is used to control for a likely confounder. And it's very similar to what we talked about. I think it was way back on page 8, if I'm not mistaken. Let me just see if I can pull that up for you. Yes, it was back in page 8 where I said there's, at the bottom of the page here, when we were talking about stratification, I said there's two ways to control for a confounder. One is stratification, like above, you stratify on what you think is the confounding variable, like we did in this example. We saw that smoking was the confounder. It wasn't really lighters causing cancer, it was smokers smoking. Stratification, or another way to do it is modeling, which is including the confounder as an independent predictor variable, an x variable, in a regression model, as we're going to do in chapter 28. And that's where we are now. So let's look at this example. So that says there's two ways to control for a possible confounding variable in observational data: stratification, that was, so we looked on page 8, and modeling, which we'll talk about now. So we're looking at this simple case where this is from our survey data, from Stat 100 survey data from a while ago. From I'll pull it up in a minute and you can see the data. It's from spring of 2013. But I often ask this question about what's your shoe size and how many pairs of shoes do you own? So this is shoe size and shoe number. And I often get this, usually this negative correlation, which kind of doesn't make sense. Why would the size of your shoe be causing you to buy less? Why would the bigger the foot you have cause you to buy less shoes? And the smaller the size of your foot cause you to buy more shoes? It doesn't really make sense. I mean, it's not like shoes cost, or you pay a certain amount per length of shoe or amount of leather or whatever. They cost all about the same. So this seems kind of unusual, and it doesn't look like a causal relationship. So we thought there might be a confounder. Does anybody here think of what might be driving this? So a confounder would be causing both the shoe size and the number of pairs of shoes people own. I should put the y variable here. The shoe size is the x, so let's put this here. So this is x. Is shoe size causing people to buy, the bigger your foot, the smaller the number of shoes? Or is it something else? So I'll put shoe number here, which is the number of pairs of shoes you have. Okay, so that's x and y. So can anybody think of something that might be driving this? Yes, in the back? That might be that, okay, so what he's saying is that bigger shoes, anybody who has a big foot here, size 15 or something, they're less common and they're harder to buy. So that would be causing you to buy fewer pairs of shoes. Yeah, that could be the confounder, that they're causing you, but would they be causing you to have a bigger foot? That would be a causal link. It would be a great causal link. What he said was that, yeah, if the availability. So that would be a causal link. That if you have a big foot, depending on your shoe size, that changes the availability, which changes how many pairs of shoes you own. That makes total sense as a causal link. Great. Can anybody think of a confounder that would go fit in there? Gender. Yes, gender would be a confounder. And because what you're saying is that certainly we know that if, generally speaking, girls probably buy more shoes. Maybe boys do, but that, whoever, I think from this data, it looks like if girls buy more shoes and have smaller feet because they're smaller, gender comes first. So whichever gender you are could cause your shoe size, cause you to have bigger or smaller feet generally, and cause you to buy more shoes. Okay, in this culture, or in the data that we're seeing, that could be a confounder. So what would we do if we thought that was a confounder? We'd try to stratify on gender. And why don't I show you this picture and show you what happens? Okay, I'll pull up this data, and let's look at it. I've got to get rid of this, sorry. Okay, so what I would do is, first of all, I want to show you shoe sizes on our X and shoe numbers on our Y. And that's the data you see in front of you. And here's the regression line. So, and there's the regression equation. If you look at this regression equation down here, and it's in your notebook too, what it's saying is that for each extra shoe size, people typically buy or have 2.5 fewer pairs of shoes. That's a pretty strong effect, and it's a negative 3.2 correlation. So there's a pretty strong negative correlation there. So what if we split on gender and stratify? So let's do that. We'll split the plots. And now we've got two plots, and look what happens. You see how that relationship disappears. In fact, the slope, if anything, is slightly positive, but very, very small. Remember, we saw a slope before of like 2.5 pairs of shoes, and here we see about 0.1 pair of shoes or 0.3 pairs of shoes. So it's a very minimal slope, and it's not negative. So here, I'll show you what's happening. If we combine these plots, what's happening is that these purple dots represent the females in Stat 100, a lot more females, and these yellow ones represent the guys. And you can see there's two fairly distinct groups of students here, and we could either show, and they almost have equal slopes here, slightly equal positive slopes right here. So these are the stratified equations right here. And so when we split, that strong negative correlation goes away that we saw here. So you were right. That was the confounder. Whoever said that gender is the confounder. So let's show that. Let's write it down. So let's go back to our document camera, and let's just so you can remember this, let's do a very exaggerated version of that plot you just saw. So this is really exaggerated, but it helps you remember what confounding is. So this is shoe size, and this is shoe number of pairs. And basically, we have two distinct groups. I'm going to draw an exaggerated version here. We have up here with small feet, but lots of shoes, females. And we have down here with larger feet, but fewer shoes, males. But inside each, there was basically no relationship. It was basically pretty flat. It certainly wasn't negative. It looked like this. But so this relationship, this causal relationship that we thought existed, maybe, here's a good explanation for it, that it was availability, isn't strong enough or doesn't isn't coming into play here. Instead, this is completely an artifact or a confounder. It's a misleading overall correlation because we should have broken it up into two groups. And this is what's creating the regression equation, sees them as just basically two clumps, and is fitting a negative correlation, which isn't true for anybody. And that's why it's confounded. Confounded means mix up, bogus. And so if you just look at this, you think there's some kind of relationship when really there isn't at all. There's no causal relationship. Does that make sense? All right. So it disappears. So we suspected gender was a likely confounder, causing both females to have smaller feet and to have more shoes. So we broke the population into males and females and saw the relation disappear. So we stratified by gender and the relationship disappeared. Now, and these are the stratified regression lines. And this one is the males, and this one is the females. Maybe I should write down what they were so we don't forget. When we force their slopes to be equal, they're almost equal. When we force them to be equal for males, we got two different regression lines here, the stratified ones. And here we said, okay, our predicted Y, which is our number of shoes, is equal to 4.255 plus 0.2472 times X, which was just the shoe size. Okay, that's what we got here. And here we got for females a different intercept, a higher intercept. We got 17.77, and we have about the same slope. We force it to be exactly the same, slightly positive. Okay? So this Y, just to remind you, is what? Number of shoes. And this X is shoe size for both of them. Okay, so that's what we did. Now, any questions on that? Okay. Now what we're going to do is we're going to add gender to the regression equation to show you how it does the same thing as stratifying. But first, so let's look at how gender, if you add it as an independent variable, along with the shoe size, would work to separate out the effects of each and give you the stratified equations. So let's, first of all, you're probably not used to what it would even look like to have a 0-1 variable, a categorical variable predicting a quantitative one. So let's look at what the regression line is, and you can do this on your own. This is exactly where the data is. So it's in the data program. You can search for this, and you can do this. It's just what we're doing together. Okay, so let's go here. So now what we're going to do, and we'll pick, instead of shoe size predicting shoe numbers, let's look at gender. So we get this graph that you see in your notebook, and let's think about what it's doing here. First of all, okay, so what you have to know is how we coded gender. Well, I assigned males to be 0 and females to be 1. And that was arbitrary. You can do it the other way too. I just did it that way. Males to be 0 and females to be 1. So gender's along this axis, and there's just all these are the males. And where this point is right here, where the regression line hits, is the average for all the males, and here's the average for all the females. Let's look at our statistics, and you can see that. So the average number of shoes, this isn't good statistics for that. Why? Let's go back to the other one. I just want to show you the summary statistics. Okay, so the average number of, I can get it another way. Let's go back, sorry. I have to split to get that. Okay, so let's go back. We're gender predicting shoe number, and we get the regression line. Let's just get it again. Okay, so now if I split the plots, I'll get, will this give us the statistics? Yeah. So for guys, the average number of shoes was 6.884. For females, it's a lot higher. It's almost 20. And the minimum was 1 for guys with a maximum 77, and 1 for females with a 2 for females was the minimum with a maximum of 100. I cut it off there. Okay, so now let's combine the plots again so you can look at them. And let's go back to, now that you understand that, let's go back to our document camera. Okay, so any questions on this? Good. All right, so let's look at this. And what are we doing here? All right, so this is the males coded as 0, and this is the females coded as 1. And here's our regression equation right here. So what does the regression equation give for males? Well, this right here is gender. And we coded it as x equals 0 for males and x equals 1 for females. So, what does it give for males? Well, let's just do it. For males, it's a 0 here, right? So I just get 6.884. And did you recognize that? That is exactly what? The average number of shoes for guys. So it's right here. Y bar for male is this. That's all it's doing. These are all the guys. I guess this one right up here went all the way to 77. And for females, it went up to 100. Okay? And so now for females, what's it going to do? You're just going to put a 1 in for x. So you do the same thing. And this, of course, gives you the average for females. It's right here. And can you see what this equation really is? This equation is saying, okay, the predicted number of shoes is going to be the average for the guys plus, what's this? Look at this. It's the slope as you go from 0 to 1. So as we go from 0 to 1, it's this right here. We go up by what? We go up by 12.86. So all it is the difference of the two averages. So it's just the difference between the female minus the male average. So that's the equation. Okay, so that's pretty simple. And what do you think would happen? I said it was arbitrary which way we coded it. So what do you think would happen if I switched the coding? If instead, what would happen if we just switched it? Right? So now females are 0 and males are 1. So what would the picture look like? Can you imagine? This bar would just go over here at 0 and the bars would be switched. So we'd just get a picture that looked like so here we had males and females. Okay, so now we have females equals 0. So we'd have their average up here, which would be y bar for females, which is 19.74. That's at 0. And then we'd go over to 1. And we'd have y bar for males, which is equal to 6.884. So it'd just be the same thing, except as you go over 1, you'd go down by that same amount. You'd go down by 12.86. So our equation would be what? Our equation would be when x is equal to, for females, when x is equal to 0, we'd have 19.74 minus, because we're going down, by 12.86x. Or in other words, we'd have y bar is equal to the female average, right? Plus the difference of y bar males minus y bar females. So that's just the idea of, just a simple, to give you an idea of what's going on with that regression equation. All right, so now what we're going to do, any questions on that? It's the same thing, we just get, this is the difference between the x and the averages. Okay, so you're going to play around with stuff like this and you'll get a better feel for it. But let's move on for now. And we're going to combine those two simple regressions into a multiple regression. So let's do that. So now we have two simple regression equations. One predicting shoe number from gender and one predicting it from shoe size. All right, so we're going to combine them into one. We're going to combine them into one, and let's switch. Let's see. Okay, so x1 is going to be gender. So we have one from gender right here, and we'll say x2 is shoe size. So we're going to combine this one, predicting shoe size, with this one and put them together. And what you're going to see is these betas, these slopes, you would think, oh, you're going to get the same slopes here. You're not. You're not going to get the same slopes. What you're going to see is this shoe size is almost going to disappear because of the confounding. And because these two are very correlated. Okay, so the slope of each predictor variable, and this is super important. Let me start before I even talk about it. Okay, the slope of each one of these predictor variables controls for the other variable. What does that mean? It means that, for example, the slope for gender estimates the difference gender makes on shoe size, controlling for, gender makes on shoe number. So it's the difference that gender makes on how many pairs of shoes people buy, controlling for shoe size. So that means, for example, I have a shoe size of 10. So, and women who have a shoe size of 10 would be compared to guys who have a shoe size of 10. And we'd see how much the difference in our gender makes for the same shoe size. Same with shoe size of 9, same with shoe size of 11, etc. Do you understand? So it says, estimates the difference gender makes in the predicted number of shoes owned for those with the same shoe size. So that's how it stratifies. Now, the slope for shoe size, what do you think that does? That estimates how much an increase in shoe size makes, like some comparing me with a size 10 to another female who has a size 11, how much a difference in shoe size makes for the same gender. So within each gender, how much does shoe size affect predicted shoe number? And we already saw it makes very little difference inside the gender once you control for gender, once you stratify on gender. So given the same gender, it really doesn't matter how big your foot is. And so when we put these two together and we do, now we have to do, we can't do a Z or a T analysis because now we have two slopes. So we must use what we learned, analysis of variance. Last time, that's what we used. We didn't have to use it if we only looked at shoe size, but now when you put two x's together, you must use ANOVA, analysis of variance, because we have more than one predictive variable. We have more than one x. More than one predictor variable. We have two predictor variables now. So I can show you, let's look at what we get here, and then I can show you how to do it yourself, because you're going to have to do it in the homework on our data program. So we'll go through these steps so you can see how to do it. First, though, let's see what's going on. So we have basically 3 parameters here. We have a beta naught, a beta 1, and a beta 2. So this is beta. So we're predicting 3 population parameters with these 3. All right? And if you look here, what this program ran was 2 types of test. It ran a chi-square test. And so we can look at this. There's 1,046 people in this data set. That's where this n is. It also tells you, like, the regression degrees of freedom. That's the number of degrees of freedom for the chi-square, which is p minus 1. So this is p minus 1. 3 minus 1 is 2. It's the same as the number of x's in your model. The parameters includes the intercept, but that's why it's p minus 1. You subtract off that intercept. And we got a p-value of 0%. That means it's really significant, but what was our null? Well, the null is always, remember, or usually, the hypothesis of no effect. It's easy to remember because we call it null. No effect. Our model has no effect. That means that both of our x's don't make any difference. The ones we're trying to predict, the gender and shoe size. Null says they don't make any difference on how many pairs of shoes people have. Of course, the intercept's going to make, the intercept is just, if you fit a model, the intercept will just be the average. If these made no difference, they'd be the average number of pairs of shoes. So we're not testing that beta 0. We're just, the null is that our x variables, the slopes for the predictor variables, beta 1, is equal to beta 2. They're all 0. That's the null. Not just one of them is 0. So they're all 0. And so what do you think the alternative is? They're not all 0. Or at least one of them is non-zero. So it's not all betas equal to 0. No. Of course, these are just the betas, the coefficients in front of the x's. We're not, the intercept never enters into this because you're always going to get an intercept. You're not going to get a 0 intercept until unless the average number of pairs of shoes people owned was 0. Okay, so that's what it is. And we can see right from this p-value, we're going to reject the null with the chi-squared. We have a huge sample size, so it looks like it's okay to do that. We're going to reject it big time. Remember, when the null is true, we'd expect a chi-square equal to 2, its degrees of freedom. And look what we got. This gigantic chi-squared. Okay? And if you wanted to compute it from here, it would be pretty easy. What would you do? I guess I could do it right here. If you wanted to calculate this yourself, you could say chi-squared equals, you have r, you'd have to r squared over 1 minus r squared times n. I guess the r squared's right here. I can use that. And you'll get the same thing. So if you did what? 0.259 over 1 minus that, which is what? 0.741 times n, 1046, you are going to get the same thing. Okay, so that's what we're doing here. We've had, now if you want to do it by the f, right here, and here, when you do an f, people do a ANOVA table. So let's see if we can make sense of this. ANOVA table. First of all, so here's the total sums of squares. Here's the sums of squares model, due to our model, which is a regression, and here's the sums of square error. And here's the degrees of freedom, which makes sense. What is this? This is p minus 1. Remember, where should I say? P equals 3 and n equals that. 1046. So this is p minus 1. This is n minus p. You get 1043. And this is n minus 1. And they sum. 2 plus 1043 is 1045. Then this is the mean squares, and then this is the ratio of them. And we got, look, the same p-value, of course. I mean, this is such a big sample size, they're going to be, it's not exactly 0. If you went out to lots of decimal places, it's essentially 0. It's never exactly 0 because the curve never crosses the x-axis. But it's rounded to 2 whatever decimal places, 4 decimal places, it's 0. And if we wanted to compute this one, the easy way with the r squared, we could do that. And you could say, I just want to tie all this together. You could say f equals r squared over 1 minus r squared. So far, that's exactly the same. But instead of n, we're going to say times n minus p over p minus 1. So what do we get? We get exactly that, 0.259 over 0.741. But then instead of 1046, we're going to have 1043, right? Because that's n, and we're going to say n minus 3. So at this point, you'd have something very, very similar, just a tiny bit smaller than that. But we have to divide, now that we have 3 parameters, right? So you divide by p minus 1, so you divide by 2. So we get a statistic that's about half that, which is our f statistic. And that's why it looks really different. Even though, as I said before, as n is large, they're pretty much the same curve. It's just shifted over. So we're going to get 182.3. What I mean, that's very hard to see, but you have it there. 182.3. It's the same thing. What I mean is you're going to get the same p-values, unless you take out to a really far in the decimal place. And then do you know which one would be a bigger p-value always? F and T. F and T always have bigger p-values because they have fatter tails, right? In fact, I should have written that. Just excuse me for a minute. Let's just go back to page 131 and write that down there because I should have done that back up. So just write that at the bottom so you remember it because it will help you to remember things. So F, here we were comparing the F and the chi-squared here. So let's go look at that. So we'll say F and T. See how it's like fat, spells fat, have fat or tails. So p-values will always be bigger because that measures the area in the tail. If you take it out to enough decimal places. Bigger than what? Corresponding chi-squared and z. Assuming everything else is the same. So that's an easy way to remember it. Bigger p-values, meaning what? You're less likely to reject the null. You need more evidence to reject the null. What? Are always bigger than chi-squared. That's a chi-squared and t. Okay? And did I make a mistake here? Does anybody see it? Chi-squared. That's the chi. That's the letter chi. Oh! Gosh! Thank you. I'm so dense sometimes. I know I shouldn't say that, but it's about myself. And I didn't say the word dumb. I said dense. Okay? All right. I know I could get in trouble for saying bad words, even if it's about yourself somehow. All right. Now let's get back to what we were doing. So I don't want to get distracted, and look at what we're doing. So what I wanted to show you now is, first of all, 2 things. look what happened to here's our regression equation right down here. So this is what we got. How did I get this from here? I'm just looking at these slopes here. And so I'm saying, okay, these are the slopes. They call them slopes here, but the intercept is the first one. And this one, so this is beta, not beta, B1 and B2. And here is the regression equation right here. So now, look what happened to the shoe size. It went down to just a tiny little, from making a big difference, a slope of for each extra pair of shoes, people bought on the average minus 2.5 pairs, 2.5 less pairs. Here, they bought on the average a quarter of a pair of shoes. That's not going to help you much. It's very tiny. And it's insignificant. Look at the p-value for it. It's insignificant. That's for a one-sided. For a two-sided, it's even more insignificant. So this is not significant. Only gender is significant. Shoe size is no longer significant. It hardly matters once shoe size is included in the model. We saw that. It was a nearly flat slope. All right. So why don't we look at this? Let's go to, and what does this even look like? And we should picture what it looks like. First of all, this is an equation for what? It's no longer an equation for a line. You have two variables here. You have 3 points. It's a plane. So now we have a regression plane. So it might be helpful to visualize it before we go any further. So, and also to help you with your homework, let's look at how to do this, where I got this from. So let's go back to the document camera and back to the PC. And what we're going to do now is go back to home and go to multiple regression, or regression here, instead of just a scatter plot. We'll go to regression. And we're going to choose as our y variable the shoe size, and as our x variable, we're going to choose both gender and shoe size. Excuse me, this should be shoe number. How many pairs of shoes you have. And we're going to choose gender and shoe size. And so there we have our coefficients. And here's the chi-square result. And if we want to show the ANOVA table here we get the other result we got with the F. So any questions on that? Or how to interpret those tables? All right. Now let's look at, don't get confused by this. These Z statistics we're going to do for individual slopes, right? But for the overall, to see if there's anything in the model, we do an F stat or a chi-squared. Now let's go to what it would look like. So let's go to, let's see, 3D scatter plots right here. So we're going to choose as our y variable shoe, number of pairs of shoes, and gender and shoe size. So now we've got this 3D plot here, and let's look at the regression plane, because now we're talking about a plane. So can you see which one? So you have two groups of people here. These are the females, and these are the males. And this axis right here is shoe number. So people are, the predictions lie on this plane. Now, what is the slope for shoe size? It's very small. It's that tiny, slightly positive slope. Whereas right here, along here, is this comparing, this is our bigger slope, comparing males to females. So now if you want to look at, okay, so what's this? This is x1 for fixed values of x2. So this is how much a difference gender makes for people of the same shoe size. So everybody here has small feet. There's hardly anybody. These pink lines are gender how much, this has that big slope that we got of 13.51. Whereas the other way, these are, well, there's only two of them because this is controlling for gender. So here, everybody's a man. So it tells you how much, there's just a tiny little difference, a tiny little slope that it makes for each additional shoe size, how many slightly more pairs of shoes you'd own on the average, but it's not significant. It's not different from zero. It's just really due to random noise. It could easily have gone, it's not at all significant. Okay? And that's the same here. Does that help you understand it? If you want, you can kind of rotate these to help you it's hard to see. This is, seeing things in 3D is like, some people can do it, some people can't. But if you do the right rotation, you might be able to see it better. So you can play around with that. But we're in 3D now because we added, and once we get another predictor variable, we won't be able to visualize it at all because we can't visualize 4D. Okay, so let's go back now to the document camera. So let's interpret this. So how do we interpret this regression equation? So what does it simplify to for males, and what does it simplify to for females? So let's look at it. Okay, so for males, what's this going to be? Well, for males, we have to remember how it's coded. Gender is coded as 0 for males. So for males, G is equal to 0. All right. So now we can say for males, you're going to have 4.255 plus 13.51 times 0 plus 0.2472 times X shoe size, X2. There's no gender variable. This is just going to be, this is your equation. Because you don't need a gender variable. Now once we stratified it, it's just males. There is no gender variable. So we just have this. Okay? And X2 is shoe size. And Y is the pairs of shoes. So we'll do the same for females. And now here's the difference it makes. Gender makes for going, comparing males to females, females have on the average 13.51 more pairs of shoes. And we're multiplying by 1 here. Plus. Okay, so what we notice here is two things. First of all, let's simplify this. We'll add this together, and females have a different intercept. When we add those two together, we get 17.765. And we have this tiny little slope here. But the point is that multiple regression forces the same slope for all levels of the other variable. It forces that. So we have the same slope, but different intercepts. Different intercepts. Okay, and notice this should be the same as the stratified equations we got. Let's check it on page 135. It's the same as these. Okay, it's the same exact, see? When we force the same slope. So we just got these same things. In fact, this is you're going to have a lot of homework on this, so maybe we should do a homework. Let's look at the summary now, and then do an eye clicker to help you with this. First of all, so let's see if we should do that. I think we should do the eye clicker question is going to look like this. So this is like homework practice right now, and then we can do one too. All right, homework practice. So why don't I give you those two stratified equations and see how you would come up with that multiple one. So the stratified equations, given that males, so here's two stratified equations. So we have 4.255 plus 0.2472 times shoe size. So that's times x. That's for, and then for females, we have what? A different intercept but the same slope. So the intercept is 17.77 plus the same slope. All right, so that's for females. And now the question is going to be that you have a lot of homework practice on this, and I'll post it as soon as this afternoon, as soon as this lecture is posted. So we want to combine it into one regression equation that's a multiple regression equation. That's the same thing, but we're going to say, so what intercept, fill in the blanks here, plus what times x here, plus something times, we're going to add this gender. And we're going to code gender as, for males, it's going to be, so G equals 0 for males, and G will be equal to 1 for females. So how would I do this? Well, the way to think about this is fit the males first. Okay, here's the males. Fit them first, because G equals 0 for males. So when G is 0, we want to get that equation right there, right? So we might as well, and besides, they both have the same slope, so we could just put that in right away. So for both equations, we want the same slope. Now, for males, when that's 0, we want that intercept, we want, right, 4.255. So that works for males. Now, how can we change it to work for females? That is where, well, females, when G is equal to 1, so when we put a 1 in here, think about putting a 1 in here. So now, what do we want that to be? 4.255 plus what? We want it to equal 17.77, these two together. Once we put a 1 in there, so I basically want 17.77 as my intercept. But I have this already, so I have to subtract it off. Right? And that will leave, so that equals 13.515. So that's the multiple regression equation that we should have gotten within rounding, right? Let's look. Is that what we got? Yeah. That's what we got right here. Shoe size, yep. I put gender second, but it really doesn't matter. Okay, do you understand? So let's try an iClicker just to make sure, and this iClicker is copied directly from your homework, just to make sure you understand what you're doing here. So let's go here. Okay, so I'm going to start this. It's kind of hard to see this, sorry. So these are your two groups. Right here you have two distinct groups. And there's confounding here. There's confounding. This clearly isn't good, this overall regression equation. So we don't want to use that. Instead, we want to go into 3D and add a variable to account for, to take care of this. Because it's nice to have one single regression equation rather than two separate ones. That's the point. So we want one equation, so we're going to move into another dimension. We're now in 3D. This is bogus, trying to do it in 1D, because that's going to give us a wrong answer. And all we're trying to do right now is figure out what goes in there, given those two. So here's your choices, and decide what goes in there. Are y'all voting? Okay, I'm going to stop it and see what you said. Great. Perfect. Okay, so we've got that taken care of, and let's move down to the next one. All right, now what's the intercept? You have to pay attention to this coding here. We know 2.3 was correct for the slope. Now you want to figure out this blank right here. What do you want to put in there? Try to get this out of your way. Okay, I'll just let it go a few more minutes and choose one of those. Not a few more minutes, a few more seconds. Okay, let's see what you chose. Great, terrific, very good. Okay, so now we're going to do the last one, which is right here, and I'll start this. Now, what's going to go in here for the G? We know this one. And you want to end up, when G is 1, you want to end up with this. Sorry, this is in your way. Okay, just 5 more seconds. Okay. Great. Perfect. You got it. This is amazing. Very happy. So that you'll be in great shape for that homework. So now let's go back to the document camera and move on. So I just want to alert you to that there's some important points here, and this one is key, that multiple regression forces the same slope for all levels of each variable. All right? So what happens if they really have different slopes? What can we do? That's what we're going to talk about now in this chapter. We're going to add what's called an interaction term to our multiple regression. Okay? So multiple regression forces the same slope for all levels of each variable. So all the levels have parallel slopes. This is really important, so I should highlight it. In the last example, that was appropriate because both the males and the female slopes were about the same in the stratified plots. But what if they're not the same? What if the relationship between shoe size and the number is different for males and females? So here, I used to, in the old days, get plots that looked very much like this, where there were different slopes for males and females. And this was one of the last years I got it. This is fall 2012. And so here's this really strong negative slope here that we have. And here's our stratified regression equations. And for males, this is the males, it's pretty flat. But for females, there used to be, certainly in my day, there would have been this negative slope, sort of, I call it the Cinderella effect, where if you had big feet like mine, you just dreaded going to a shoe store because it was considered very ugly. You didn't want to draw attention to your feet. It was painful you tried to squeeze your feet into small shoes. It's kind of, remember in China, they used to bind women's feet. So this is very culturally specific. So it looked like this, a negative relationship here that held up. Now that's disappeared, thank goodness. So these are stratified. These are your stratified regression equations. And they do have different slopes. So So now what do we do if we want to do this? When the effect of one X variable, shoe size, on shoe numbers is different. It's flat for males and different for female, depending on the value of the other X variable, gender. That's called an interaction effect. And adding an interaction term, which is a multiplicative term, you'll see in a minute, it's not an additive factor, it's a multiplicative term. We're going to be multiplying two slopes together, allows for non-parallel slopes. So let's draw the picture of this, just so you get a visual. So the visual, exaggerated again, is we still have this confounder. We have two groups and a confounder. So females are still up here, and males are still down here in the exaggerated version where we're pretending there's no overlap, right? And this is shoe size. And this is number of pairs of shoes. And with males, there's nothing. There's basically no slope. It's very, very flat. But with females, there's a slight negative. Not as big as this one. A slight negative. Slope negative 1.17, not negative 2.7. So it's a slight negative slope. We see it, and we want to, they're different. Okay? This is a small negative slope. Now the overall is still highly confounded because it's a sharp, it's a bigger, much bigger. That's overall, it's really confounded. But we want to allow for these two different slopes. So there's an interaction term. Interaction because there's an interaction between group and the slope, because we have different slopes. And there's confounding still. There's still confounding too. There's confounding, which is completely different. There's confounding too, because why? We still have group membership, gender, which affecting both things. Both shoe number, the Y variable, and shoe size. So we've got both going on here. All right? So how are we going to deal with it? Well, we're going to add an interaction term. So let's do that. So here's multiple regression with the main effects and an interaction term. So the main effects are what we are, just B1 and B2, and then an interaction is when we multiply X1, those two together. All right, so let's draw this. Let's see, so we'll have B1 and for X1, and B2 for X2. And then we have this multiplicative effect here. That's both of them together. Okay? So why is the predicted number of shoes? I think it'll be easier to explain this if I change this to X2 and this to X1. Sorry. So X2 is going to be gender, and X1 will be shoe size in this one. All right. So, now, so since, let's do this. So gender right here is going to be X2. So it's going to be 0 for males and 1 for females. All right, now here are our stratified. You see they have different slopes. So these are our stratified. So this is X1 and X1. There's no gender in these. This is just the X1. We're doing X1 as yellow. These are all yellow. Okay. And let's see what we want to do here. All right, so we want to know how to fill this in, first of all. What are we going to be doing here? And then we can think about it some more and do some eye clickers. All right. So how are we going to match these up here? Well, it's the same way, but now they have different slopes here. So let's think about this. First, let's color code it because it's so confusing. So this is x2 and this is x2. And remember, right here, for males, it's going to be equal to 0. And for females, that x2 is going to be 1. Okay, we don't have it here. We have it here. So the first thing that we should do is what? Don't you think the first thing we should do is do males? Because when you have males, this is a male equation, these disappear. 0 times anything is 0. So we just have this equation right here. So we should just put this x1 here for x1. And this. So let's fill that in first. And that will give us when males is 0, that's perfect. Our multiple regression should give us that. Now, what about when, for females now, what should I do? So now for females, we're going to have a 1 there. So let's just concentrate on this intercept here. 1. When you put a 1 in here, there's no x's anymore. It's just a number. It's going to be the intercept. So we want it to be this. So that's what we want it to be. So I would write, I want it to be 29.24. But I already have this. See, this is going to be a 1 here. So this just be a number, no x, and I'll be adding it to that. So I have to subtract that off. So I just want that difference between the two intercepts is what's going to go here. It's just the difference between the two intercepts, which is 23.391. Do you understand? Okay? Because when you go from, and now what do you think this is going to do? So we've got everything done except I want this slope. Right now we've got that, and what I want to get that, I want negative 1.17. So but I already have that, so I want to subtract it off. So all I'm doing is taking the difference between the female slope here minus the male slope here. And I did the same for the intercepts. So when I did that, I got negative 1.18255. All right, so that's what we got. Let's check and make sure that's what again, we have to do ANOVA right here. And ANOVA gives us this fitted, these coefficients here. Now we have 4 parameters. Here's B0. Now be careful here because I switched the coding. So this is actually B1, this is B2, and this is B12. That's the interaction effect. And so let's match them up. Yeah, 5.849. That's correct. That one within rounding is correct, and that one within rounding is correct. They just went, okay. So that's how we got those. And of course, again, our null is that all the betas in front of x's, all these terms are equal to 0. In the population, in our sample, of course, we got something, right? That's it. And we can see, again, we reject that null. And the alternative, again, is that not all of them are 0. One of these is significant. And which one turned out to be significant? Look at this. Look what happened. Gender is significant and the interaction is significant, but shoe size disappeared. Shoe size disappeared here. So this one's significant and this one's significant, but not that one. And so which variables are significant? Only gender and the interaction term. So shoe size hardly matters once gender and the interaction term are already in the model. And again, you can do your chi-squared and your F from the same way we did before, and you'll see you'll get these same statistics. It's a little, so what else should we do here? I think we need to do an eye clicker here, because you have something for homework that's just like this. So let's practice that, okay? So let's go to the eye clickers. And go to our next one. I didn't give you any. Whoa, did I not give you any? I'm really sorry. Did I not give you any answers here? What is the slope for G in the oh, that we already did. Okay. Here we are. We're on their new question now. Sorry. Okay, so this is our new one. So now we have an interaction effect. Can you see that? We have, look at this. We have this group that has this slope, and this one has this. A huge interaction effect here. So we want to fit, and here's their two equations. So fill in the intercept in x. So which one do you want to do here? Do you want to put this one or this one? Choose one of them. The key is to fit this group first because G is 0. So this whole thing doesn't matter. So pretend that didn't exist and fit this one first. Okay? All right, we're going to stop it and see if you did it. Great. Okay, so now let's do the next one. Okay, now what is the G slope? Just do the G. It's one of these two. Which one do you think it is? You want to end up with 10.5 there. Okay, y'all finished? Choose one, just 5 more seconds. Okay, stop, and let's see if you got it. Great. It is A, because you wanted to end up with 10.5. 10.5 minus 4.2 plus 4.2. Now the last one you're going to do, and let's do that. We'll start that. And then you'll have the whole equation. So basically, you're just changing, you want this x to change to what? To the blue group, to -2. When you put a 1 in for here, you're just going to say 2 plus what equals -2, basically. So you got that, I hope. And let's stop it. And make sure you get it right. Great. Okay, so that's perfect. So now you can do that homework, and let's just go back to the document camera and make sure we've looked at all this. So we're going to reject the null here. Reject null because P is less than 5%. Same here. We'll reject because P is less than 5%. Which variables are significant? We've got that. Now our last question right here, I think we're going to save this. I have this on the homework, but I think I'll take it off and put it on the next homework, and we'll start here next time. So that's all we need to do for today.